Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon, everyone here, and good afternoon, everyone. Good afternoon for the audience online. So, welcome to the IF Colloquium. And today we are pleasure to have Professor Boris Gänsicke as our speaker today. And let me introduce him briefly. He graduates master's degree in physics from Technische Universität Berlin, and then he continued his Ph.D. in physics and astronomy from George August Universität Göttingen, Germany. And today he will tell us about in the topic of how the world will end. Please welcome our speaker.
Thank you very much for the invitation. It's a great pleasure to be here. And the talk that I will give today is, I think, a little bit different from the topics you have had in the past. It's a redshift zero talk. And so there's very little strings and very little cosmology involved. But I hope it will be interesting anyway. And the topic is how the worlds will end. And it's a plural because I will talk about both something that we may learn about our solar system as well as about other exoplanetary systems. I will split my talk into roughly 4 sections. And the first part is I will give a brief summary of what happens to planetary systems as their host stars evolve off the main sequence. And I will then outline a couple of observational signatures of planetary systems around evolved stars, around the white dwarfs. I will show that we can use those systems to measure the abundances, bulk abundances of exoplanetary systems. And then finally, I will briefly talk about the discovery of an actual full-size planets orbiting very closely around the white dwarf. And I will sprinkle in little bits of theories just to keep you awake. So let's go into the first section. The first exoplanet was discovered by radio velocities orbiting a solar-like star in 1995. So it's just 30 years ago, less than 30 years ago. But today we know that pretty much every star in the sky has planets. So having planets is totally normal. And that's a very big jump from 30 years ago, where we knew the planets in the solar system and we didn't know how planets form. We didn't know how common it is. It is very common. And so if we then think, well, the stars that we see today have planets, that means that the stars that have left the main sequence have become white dwarfs. They may have had planets in the past. They very likely had planets in the past. And the question is, can we see signatures of that? So the question I will talk about in my talk is like, what's the future of planetary systems? And then what's the future of the solar system? And what can we learn from those evolved planetary systems if we find them and can observe them? So let me just go through a quick summary of what will happen in the solar system. So stars are born from molecular clouds, condense, ignite hydrogen fusion, burn hydrogen to helium, and they spend a very long time in a very stable state, core hydrogen burning. We call that the main sequence. And the sun is at the moment roughly halfway through its main sequence lifetime. It's about 5 billion years old, another 5 billion years to go. And then from the remains of the molecular or cloud that formed a star, dust that is in there coagulates and forms planets. So in about 5 billion years from now, the sun will run out of hydrogen in its core, and so fusion will cease in its core, and the sun will start to expand into a red giant. And at the same time, the core will start to collapse under its own weight, because stars are in equilibrium between gravity going inwards and pressure going outwards. In the sun currently, it's thermal pressure that balances gravity. Once fusion stops, the core shrinks because thermal pressure is no longer there. And it's eventually the pressure of degenerate electrons, because the electrons get so close together that the electron degeneracy holds the star from further collapse. And so this is the solar system drawn to scale. We have 4 rocky planets, and so we are on number 3 here. Then we have an asteroid belt, lots of small, medium-sized, and fairly large-sized, couple of 100-kilometer rocky bodies. And further out, we have giant planets, which are mainly composed of gas. They may or may not have a rocky core. We don't know exactly. And it's drawn to scale in units of solar radii. So I'll now jump forward by a couple of billion years to the stage of the red giant. And so if I go back and forth, you see 2 things happening. One is that the sun becomes a red giant and it evaporates. Mercury, Venus, probably the Earth. We are not quite sure if the Earth will be engulfed or can just about escape being burned up. But the other thing that you notice is that all the orbits widen. The reason for that is that the sun will lose about half of its mass while it becomes a white dwarf. And as the mass in the center reduces, all the orbits of planets, planetary bodies going around it, widen by about a factor 2. The mass loss is relatively slow compared to the orbital timescale, so we think that the orbits expand adiabatically. Okay, so then we just wait a little bit longer until the planetary nebula that the sun leaves behind disperses, and we will be left with a white dwarf in the center of the solar system that will have cleared out roughly 1 astronomical unit in area, radius, and it will be orbited by Mars, a rocky planet. There will be an asteroid belt, small rocky bodies, icy bodies, and then further out we have giant planets. Now, we're pretty sure this works in the solar system. Lots of dynamical studies have demonstrated that that is the future that the solar system awaits. So the question then is, if this is what happens to the solar system, and we study stars that are already white dwarfs, they will probably have had planetary systems in the past and may have planets still, but is there any way that we can detect those systems? Now, the first thing that you would think is, well, a star evaporates everything within about an astronomical unit or 2. And so all the residual planetary system is very far away and would be very hard to detect. But you've got gravitational interactions. Jupiter in the solar system is a very massive body, and it will gravitationally perturb the orbits of other bodies and may kick them on eccentric orbits towards the white dwarf or eject them. If they get ejected, it's not good for us, but if they get on a trajectory close to the white dwarf, we may have a chance to detect them. So Second part of my talk, I will talk you through several methods how we can detect evolved planetary systems around white dwarfs. And there's very little you need to know in terms of details about white dwarf physics or structure or so on. The one key aspect is white dwarfs are small. They're roughly the same size as the Earth, but they have about half a solar mass, 0.65 solar masses on average. And that means they have an extremely strong surface gravity. And then as a consequence of that, they become chemically stratified. So on the left-hand side, you have a logarithmic cross-section through the white dwarf, where the core is down here and the atmosphere is up here. The white dwarf itself is composed to about 99% by mass of carbon and oxygen. And carbon and oxygen, why that? Because you burn hydrogen into helium, and then helium into carbon and oxygen, and then fusion stops in most stars. Those are the heaviest elements. They sink into the core and form the core that is sustained by electron degenerate pressure. And you have a little bit of helium and a little bit of hydrogen left that float to the surface. And so that means if we observe white dwarfs spectroscopically, we expect that the spectra contain only signatures of hydrogen or helium, or maybe a mixture of two. There should be no elements heavier than hydrogen or helium in the spectrum of a white dwarf. However, going back in the history, it turns out that the earliest sign of planetary systems outside the solar system, planets outside the solar system, was obtained in 1917, so over 100 years ago. The data was obtained, but it wasn't understood what it means. Now, all of you are fairly young, and you may not remember that there were times before we had electronic detectors. People in the past used photographic plates, and what you see here is a photographic plate, and that means it's a negative. I think the laser pointer just stopped.
You just point out, it just digital.
Oh, okay, yeah, right. So it's a negative of a spectrum. You have here in between these two broad sequences, the actual spectrum of the star. There's two regions where there's light missing, and these are lines of calcium. Now, calcium is heavier than hydrogen or helium and shouldn't be present in the atmosphere of a star. However, back then in 1917, Van Manen, who obtained that spectrum, he didn't know what he was observing. He was simply observing stars that have large proper motions that move fast across the sky. He measured the parallax of that star, found that it is very nearby at a distance of 4.4 parsec. It is also very faint, and he then concluded that this star is the faintest, intrinsically faintest F star ever known. Now, F stars are stars a bit like the sun, a bit hotter, a bit heavier. What he didn't know at that time is that he had discovered a white dwarf. It's the third closest white dwarf, and it was the third white dwarf to be discovered. And in this diagram, you see a modern spectrum. So this is the flux of the white dwarf, and this is wavelength in angstrom. And you see very strong lines of calcium, magnesium, and iron. Now, as I said before, white dwarfs should not contain any metals. And to demonstrate how quickly material settles out of the atmosphere, I have a video here. What's shown, just focus on the top diagram, top panel. What is shown in gray is an observed spectrum, is data. It's a white dwarf. It has a lot of structures. All of these features are from metals in the atmosphere. And the red line is a synthetic model spectrum. So we model the atmosphere of a white dwarf in a computer code with all the relevant atomic physics, molecular physics, equation of state, and so on, to then calculate the emerging spectrum. And we adjust the parameters, the temperature, the surface gravity, and the chemical abundance until we get a good fit. In the top right corner, I have a clock that runs in millions of years. And so this is today, and I will now turn on gravity and downwards diffusion. And you see, as time progresses, within about 1 million years, all the lines have become much, much weaker. And that is because the metals simply sink down under the influence of gravity, and they're no longer visible from the atmosphere, which is the top layer from which we get photons from the star. Okay, so let's just carry on a little bit longer. And then in 2 million years, if you look just at the blue part, you may say, well, that looks quite similar to the spectrum you shot in the previous slide. And so, if we wait a little bit longer, after 5 million years, the metals are gone. The age of this white dwarf, the time since it formed as a white dwarf, is about 5 to 6 billion years. So compared to a few million years, this star is very, very old. And that means on the cooling age of that white dwarf, the metals instantaneously, almost instantaneously. And so that leads us to the question, we detect metals in stars, but they should be gone on astronomical timescales tomorrow. Like a million years is tomorrow for this star. And that means they must be externally provided. They must be accreted onto the white dwarf. This has been long known and was a big problem in astronomy to answer that question. And that brings me to the second signpost of evolved planetary systems, that's dust disks. So in the late 1990s, infrared detectors became available and more powerful. And Ben Zuckerman and collaborators from UCLA discovered an infrared excess at the white dwarf. So here you have a spectrum in wavelength microns, flux. The blue part is a white dwarf. You see nice strong lines of hydrogen. And the infrared part has a very large flux excess. And that corresponds to dust of a temperature of about 1,000, 1,500 Kelvin. And then in addition, you see a strong feature on top of that black body-like emission. And that feature comes from dust in the form of olivine. So mineralogists can analyze that feature and can say what type of mineral we see there. And on Earth, we have the same mineral. It's silicate, and we find it, for example, in Hawaii on a beach. It's called olivine. And then all tying together all these aspects, Mike Jura, also from UCLA, came up with the idea that, well, if we have an evolved planetary system, and we have small bodies, asteroids, moons, comets, that get perturbed by larger bodies, planets like Jupiter, perturbed on an eccentric orbit that takes them very close to the white dwarf, they will be tidally disrupted because of the strong gravity. And they will eventually shred into small particles, may have collisions, and form a disk of dust around the white dwarf. That dust eventually accretes onto the white dwarf and explains the metals. So that was the framework developed around 20 years ago on the base of 1 or 2 stars. Now, all of you know that for us, publishing papers is a very important thing, but it's not just publishing papers. You want citations, because that is what tells you the impact of your paper. This is a figure from the original paper, infrared excess in the star. It's a paper in Nature, and that's the citation rate. Now, if you were the authors, you would be a bit disappointed because you would think a paper in Nature should do much better in terms of citations, but by around 2000, this paper was forgotten. However, you should never give up. So around 2000, NASA launched the Spitzer spacecraft, which was a space telescope taking infrared data. And Spitzer identified many, many similar systems. So suddenly people went back and were like, oh, wow, this was a really important paper. And it means sometimes when you publish a paper, you're ahead of your time. And you discover something that nobody else can make use of because you're just ahead of your time. And maybe 5, 10, 20 years later, your work may become really important. You just don't know. Okay, so tidal disruption is a topic that comes up very frequently in astronomy. And in this context, I just want to spend a few words on that. And in the simplest form, when we think about tidal disruption, we think about the Roche potential. So we have 2 masses, M1 and M2, that go around the center of mass. In that case, then the potential is simply given by the gravity of the first object, the gravity of the second object, and then you have a rotational potential, centrifugal potential, because the 2 objects go around each other. And you can calculate equipotential lines, which are shown here. This goes back to Edouard Roche and Lagrange, who solved these things, these equations. And you find that you have equipotential lines that enclose both masses, and you can transfer material through what we call the inner Lagrangian point from one object to the other. So this is the simplest form of tidal disruption. And we can calculate that in that expression, the orbital period at which an object will fill its Roche lobe and start mass transferring is simply a function of its average density. And it's that expression here with a density in kilogram per cubic meter. If I take the density of rocks, asteroids, 3,500 kilogram per cubic meter, plug that into that expression, I expect that a rocky body should fill its Roche lobe, start tidally disintegrating at an orbital period of around 5.5 hours. And that primarily depends on the density of the body that we are investigating and not the type of object that it orbits around. And now, if we ask 5.5 hours, we have a white dwarf sitting in the center with a mass of 0.65 solar masses or so. What is the radius at which that will happen? So what's the radius to which an orbital period of 5.5 hours corresponds? We find that it's about a solar radius. Okay, so these two numbers are important because they will come up later on. Reality is more complicated because real asteroids, they have internal structure, they may be clumpy, they may have internal strength, they may develop cracks. And so these are ballpark figures. Reality may be much more complicated. Now, I said in the solar system, if we expand the solar system, if we expand the orbits of the planets because the sun loses mass, and in the solar system we think this will happen in a stable fashion, we can do that for all kinds of initial conditions. And here's a set of simulations that we were running with an n-body orbit integrator, where we have a star with a certain number of planets, we have time going in this direction, and we have the pericenter of the planets going around the star on the y-axis. And the area coded in yellow is the main sequence, so that's the star on the main sequence, hydrogen burning. Then it goes through a short giant branch phase and then becomes a white dwarf. And so you see, for example, in this panel here, we have 4 planets going around the star. They are on nice stable orbits for about 3 billion years. The system goes through the giant branch, the orbits expand, all 4 planets move outwards. But then a couple of billion years later on, instabilities develop. So you get slight gravitational perturbations between the orbits of the planets, which accumulate, become chaotic, and in this case lead to the ejection of the planet that is shown in red. It will be ejected from the system. And so we run these simulations with different numbers of planets, different masses, different separations, and we get a case like this one here, where you see that the planet color-coded in blue gets on orbits which takes it very close to the white dwarf. In fact, the Roche radius, where tidal disruption happens, is down here. And so in that simulation, this planet would get sufficiently close to be tidally disrupted, break apart, and potentially form a debris disk. Okay, so going beyond dust disks, we have gas disks. And that goes back to work that I did about 20 years ago. I was studying white dwarfs for a totally different purpose and was inspecting this spectrum here where, as I said, white dwarfs have hydrogen atmospheres. And so you see in this optical spectrum strong lines of hydrogen. This is what you would expect. But I did notice that in the red part of the spectrum, there's 3 features that at first I thought are instrumental artifacts. Something went wrong with the data processing. But looking at them very closely, you see that they're double peaked and they have a very peculiar shape. Moreover, they sit in a position where we expect calcium lines. And then if you look closer, you find that there's little bits of iron here and there's magnesium in the atmosphere of the white dwarf. Okay, how do we form this kind of lines? This is actually something you will see, for example, in galactic disks. if you have a flat disk of gas that is rotating, and you are the observer in that plane, then you will have material that is moving both towards you and away. And so you get material that is blue shifted and red shifted. Now the integral of what you see, because you don't spatially resolve the disk is just a dot for you. The integral over that is this very typical double peak line profile. And it's simply the integrated intensity distribution weighted with the velocities in the disk. And that brings us to kind of very interesting technique that we can apply. So if we have an accretion disk, then we have over here positional coordinates. So that's X and Y. We have material going around the center of mass. We assume that most of the mass is in the center of the bigger Roche globe. And just ignore for now that there is a companion star here. This goes back to the original work where the methodology was developed. Now, for a point in XY coordinate space, we know its velocity. It's simply Keplerian velocity around the central object. And that means we can transform from coordinates space into velocity space. And we can tell where that point sits in Vx, Vy. And you will see that the accretion disk in coordinate space gets wrapped inside out in velocity space, because Keplerian velocities are highest at the inner edge of the disk and slowest at the outer edge. And so in velocity space, the inner edge in coordinate space becomes the outer edge and vice versa. And you can see these just 2 points translated. Now the question is, if we take spectroscopy, we can measure velocities from the spectra. Can we invert velocities that we measure into some image? And the answer is yes. It's called tomography, and the technique is similar, for example, to computer tomography in medical imaging. So here you would have a patient that goes into this tube, and you have X-rays going through the patient, and they give you a line of sight. And what you measure is the absorption along one line of sight. And then you rotate your instrument, and you fire another X-ray beam at a slightly different line of sight, and you measure the absorption. And you do that for a number of lines of sight through the patient. And from the different amounts of absorption from different sight lines, you can reconstruct a 2D image of the patient. Okay? So it may seem a little bit far from astronomy, but what happens in, for example, binary systems is that the accretion disk rotates on the orbital period. So we simply take spectra, and nature turns the object for us. And so that means we can apply that technique to disks in space. And so I have a very simple example here. Let's assume you have a disk that has a symmetrical intensity profile. It would cause this double peak line profile that I just showed. Now let's assume that you have, in addition, a bright spot that is brighter than its surroundings. And let's assume that the disk rotates in this direction. So if you're the observer here, then at one point in phase, this bright spot will move towards you. So you will get enhanced blue shift. So you will get an enhanced peak of emission on the blue side. And then this spot will move at a quarter of a phase later, perpendicular to your line of sight. And that means you will get an enhanced emission close to zero velocity. And a quarter of phase again, it will move away from you, so you get enhanced emission in the other side of the double peak line profile, and so on. And so we can use that technique, Doppler tomography, to turn data of an accretion disk that is observed in time into an image. And so what you see in the top panel is time. This is velocity, observed velocities. This is a grayscale representation. Each row is an individual spectrum at some point in time. And then in the middle, you have a reconstructed image where you see that you have a round circular structure, an accretion disk, with two bright spots in there. Okay, so that's the technique that was developed in the 1980s, application for accretion disks in binary systems, and worked very well there. Now, this disk around a single white dwarf from debris of planets, we kept observing it over a number of years, and we began to see that the line profiles change in time. And we just said, okay, let's just take that data and apply Doppler tomography. And what comes out is an image in velocity space. So this is now coordinates in velocity of a few hundred kilometers per second of the gas that creates that emission around the white dwarf. And you see that the emission is not symmetric, not azimuthally symmetric, but has a very irregular shape. Now I'll come to, on the next slide, I'll just visualize how the tomography works, and then I come to the big question. So the observer, let's assume, sits up here, and I never know in which way this starts to turn. I think it goes clockwise. And imagine you are the observer, you see this material, and you measure the velocity, and that's the observed line profile. So at this point in time, you look at the disk, and the regions of large intensity are moving perpendicular to your line of sight. Doppler shift is therefore equal on both sides, and you get this double peak line profile. And we just wait for the material to come around. And at this location, the material is moving predominantly towards you, the bright material. So you get this large enhancement here. That just illustrates how Doppler tomography works. Now, the very big question that really puzzled us for many years is the time scale on which this pattern rotates in space is around 25 years. The Keplerian velocity of the gas around the white dwarf is hours. There's a factor 10 to the 5 difference between the orbital period of the gas going around the white dwarf and an intensity pattern that very slowly rotates in space. And working through the numbers, it turns out that because the white dwarf has a very large gravitational potential, GR, general relativity precession, could be the cause for the very slow precession of that disk. So that was quite a phenomenal finding, and I just illustrate here the disk roughly in size comparison to Saturn's rings, just to give you an idea how big that is. So we went on, studied that same system, and we decided to go on very short time scales. So we obtained data every few minutes for several hours, and then went back, got a bit more, very high time sequence. And what we found is you have here these double peak line profiles that very slowly change over 25 years. But if we study the residual of the mean spectrum on timescales of minutes, we find that there is a coherent sinusoidal variation both in the total flux and in the shape. It's at the level of a few percent sitting under the mean emission. And that period is stable over several years with a period of 123 minutes. So that means we have in that system a stable clock that is coherent over several years, and a stable clock in astronomy is almost always an orbital period or a spin period of a body, because that's the only thing that can be stable of such long a period of time. And so what we assume is that this signal is a solid body that is within the gas and dust disk that isn't yet disrupted and is on a slightly eccentric orbit, and that orbit is precessing due to GR with a period of around 25 years. And so going through some hypotheses, we don't see the star itself moving, so we can exclude that there's a giant planet companion that would pull the whole star back and forth. And we can work out what is the density of a body to survive at a period of 2 hours. It's about 8 grams per cubic centimeter. The reason for that is the equation that I brought up before. The period at which a body disrupts is inverse proportional to the square root of its density. So a denser body can get closer in without disrupting. And the density of 8 grams per cubic centimeter is roughly the density of iron. So what we speculate is that there is an iron core of an initially larger body that lost its mantle and crust that is orbiting at a period of around 2 hours within the debris of the outer layers that lost before. And so that's an artist's illustration of what we imagine. And we see structures like that in the solar system. So this is, again, going back to Saturn. These are images, real images of Saturn. This is Saturn's rings. And there's a moon there. And the moon interacts with the disk and opens gaps in the disk edge. So we think that these disks around white dwarfs probably have very complicated structures and may have solid bodies in them. Okay, now the key method to find extrasolar planets is the transit method. I don't think I have a slide which explains it. So very simply speaking, if you have a planet and you observe a planetary system in its orbital plane, the planet will go in front of the host star. It will block some of the light of the host star, and the host star will dim by a very small amount. And that will happen very regular on the orbital period of the planet. And you can measure the radius of the planet from that type of data. If we have disrupting planetary bodies going around white dwarfs, some of these systems must be aligned such that we see debris going in front of the white dwarf. So we expect that we can see transits of material crossing the white dwarf. And that was found for the first time in 1995 by Andrew van der Borg, who's now at MIT. He used data from the Kepler satellite, which was designed to find exoplanets, but it also observed a couple of white dwarfs. And what you see here is a stack of light curves in times. This is minutes. And you see very small depressions in the light curves. And the interpretation from van der Borg et al. Was, this is debris which goes in front of the white dwarf. The guys obtained additional observations. They found that there's metals in the white dwarf, so it's accreting, and it has a dust disk, which is all the other signatures that I mentioned before. And then as soon as that paper came out with Dr. Ang Weyerwit, who had time on the Thai National Telescope, we obtained high-speed photometry of that star. And so what you see here is what we call a light curve. It's very fast photometry, brightness measurements. We have time in this direction. You can see timescale in minutes up here, and intensity on the y-axis normalized to 1. And you see a very, very irregular light curve. And what you see there is debris passing in front of the white dwarf. But it's not just one body, it's multiple bodies. And so that was very exciting, because from the shape and width, we could determine the size of the structures that block light. And it turned out these are not asteroids, these are not small bodies. In fact, the things that block the light, they're bigger than the white dwarf itself. There must be several white dwarf radii in size. And what we think happens is that you have solid fragments, small solid fragments that we don't detect, but they undergo disruption and eject dust. And those ejected dust covers the white dwarf. And we have multiple of these bodies. So what we did is, as an experiment, you probably can't read that from the back, but this is a light curve, just as the one that I showed before. And we observed the star every night. And you can see that there are structures emerging. There's a transit emerging. So that's a fragment ejecting dust, which blocks light at that phase. And then the dust spreads in azimuth. And so the transit gets wider. And it starts to dissipate because the dust spreads further in azimuth. But what that data helps us to do is we can measure the period of the fragment that is responsible for this transit here, and that one here, and several others. And we did that. And what we found is that for 6 individual locations where dust is ejected, we get periods of 4.5 hours. And they're identical within a couple of seconds. And those periods are stable over tens of days, which is hundreds of orbital cycles. Now, if you remember, I said just remember two numbers, the solar radius and a period of 5.5 hours for disrupting rocky material. So with 4.5 hours, we are very close to the prediction of at what point a rocky body will disrupt. And what we have shown here is that this white dwarf has not just one body, but there's multiple fragments co-orbital going around it, undergoing disruption at the moment. And so we have a large set of observational constraints that we can take to then do simulations. So we have multiple bodies co-orbiting the white dwarf. The transits are caused by dust. Activity lasts for a couple of years, and the individual transits that we see, they're stable over hundreds of cycles, and they all have very close, they're all in this at the same orbit. The periods differ by only a few seconds. And so what we did is get a n-body called Ph.D graph and start a set of simulations where we take a tightly packed n-body object, assign it a density, place it in the gravitational potential at the tidal disruption radius, and let it undergo disruption. And so we first took a body with a homogeneous density of 2.5 grams per cubic centimeter. And so you see it starts to deform under gravity. And then after a very brief time, it totally disrupts. Now this is in contradictions with the observations, because we know that these bodies are stable against disruptions over hundreds of cycles at least. And so the next step we did was we constructed an n-body asteroid with a density gradient, denser on the inside, lighter on the surface, which you have in normal planets because heavier material sinks to the cores. And so if you let that go in the gravitational potential, it takes a Roche-Loeb shape and it loses particles through inner and outer Lagrangian points, and it's stable against disruption for very long periods of time. Now, the reason for that is again the same expression that I showed before. Tidal disruption, the period at which you tidally disrupt, is inverse proportion to the square root of the density. That means a body with an average density of 3.5 grams per cubic centimeter starts to disrupt, but because it loses lower density material on the surface, its average density goes up. And that means to keep undergoing tidal disruption, it actually has to move slightly closer to the white dwarf. And so the density gradient in that body stabilizes against immediate destruction. So combining the observations with our simulations, we then worked out that we have a differentiated body sitting there with a mass of less than 10 to the 20 kilograms, density of about 3.5 grams per cubic centimeter, which is typical for rocky material, and on a nearly circular orbit. So other simulations where we introduce eccentricities where the object moves a little bit in and out of the gravitational potential also leads to very quick destruction. So, but there's so much more happening in this system. So we thought this was great success. It almost behaves like a textbook example, and it followed all the predictions that we would have had. But then we kept observing, and this is a paper that we just resubmitted while I was here. We kept observing the system. You see these very complicated transit structures. But by around 2019, the activity started to fizzle out. And by 2022, which is these two panels here, there were no transits left. So whatever happens in that system, the activity which creates dust vanished. And so if we were to observe that star now without knowing what it had done in the past, we would have no idea that this is such an exciting system where we can see this tidal disruption. And to illustrate this further, this is the kind of average absorption integrated over the 4.5-hour period. This is by how much flux is lost integrated over 4.5 hours. And you can see that it varies. This is the year 2016 to 2023. It varies from almost 20% of light lost to nothing. That just illustrates the amount of dust that was produced and has now distributed around the star. Good. So you have one system. You said that's great. That gives us a good idea. But if you find one system, there will be other systems with slightly different parameters, which you want to observe, because then you can start to do statistics and refine your understanding. And colleagues in the US published this light curve. And you may look at it and say, it looks quite similar to the system that you showed before. You have deep transits, irregularly shaped. However, they're 110 days apart. And as I said, the tidal disruption period is around 4.5, 5.5 hours. And so what we think in this case happens is that the material is still on a very eccentric orbit. So this may be a system in the earlier stage where you had an asteroid that got perturbed, is on an eccentric orbit, and when it gets too periastron, it happens to cross the white dwarf, block some light, and then goes out again and comes back again 110 days later. And then again, with Dr. Warwick, we studied a third system where we have both data obtained over 17 years, but very sparse. So this panel here shows you brightness measurements obtained every couple of days. And what you see is that the system gets brighter and fainter. And the time scale is months. And so then we obtained high-speed photometry with a Thai National Telescope, both in the faint state and in the bright state. And in the faint state, we see a very irregular light curve. And so again, what we think happens here is that you have a patch of the stream of debris with very different scales of rubble, dust, passing in front. And then there's a patch of the orbit which is clear, where there's no debris. And then another patch comes. And these patches are distributed in an irregular fashion on a highly eccentric orbit. And we think that these systems, over time, will circularize into a circular orbit, as in the first system that I showed. Now, all of this, very complex in terms of data, but the key message I want to drive home that there's a lot of very exciting physics in here, and it's something we need to work on. And so I show something that maybe is a little bit closer to things that you sometimes see. This is a simulation, an SPH, smooth particle hydrodynamic simulation, of a white dwarf disrupted by a supermassive black hole. Now, that there's a white dwarf, and this is just pure coincidence. The big difference is this is a ball of gas, and gas has viscosity. So what we see in this movie is the tidal disruption of a star that approaches a black hole in the center of the movie. And so it gets disrupted, flings out, about half of the mass gets lost, half of the mass comes back. And then with time, the gas stream interacts with itself, dissipates energy, angular momentum. Some of the gas carries angular momentum away. And over time, this will form a circular disk around a black hole. And that's what we see in observational astronomy. We see tidal disruption events where supermassive black holes in the centers of galaxies brighten up because they tidally disrupt the star. So this is where our intuition comes from, to say, well, replace the black hole by a white dwarf and replace the gas by rocky, dusty material. And then imagine you look through the material in time, and you will see these very complicated transit structures in the white dwarfs. So this is just, again, coming back to the simulations we did, is just a close-up of the N-body particles. And so we have about 5,000 particles. It's, of course, very limited in terms of computational effort that we can do. And we have no gas, and we have no internal structure. But if we let those bodies disrupt and then follow them on an eccentric orbit for a long period of time, we see in the left-hand panel, this is after 20 orbital cycles. Just think of the movie I just showed, 20 orbital cycles. The material starts to spread out along an eccentric orbit. And that comes from very small differences in the relative velocities of particles as they break off. And then with time, these differences accumulate, and eventually you form an eccentric ring filled with debris. Now, to make those simulations more realistic, we would need to add gas, because we know that you form gas close to the white dwarf, which will dampen and will help to circularize these structures. Okay, good. I just move on to a third section, and that's very quick. And that is all very good stuff, but what else can we do? So how do we know what our planet is made out of? You might think, well, we can, for example, look at the composition of lava, which tells us something about the composition of the mantle of the Earth. But we can't reach the core of the Earth, so we don't really know what's inside the core of the Earth. In the solar system, we collect meteorites, study the abundance of these meteorites, and we learn what the primordial composition of the material that formed the planets is. And then we can do computer models of planet formation with those ingredients and reproduce a planet that has the bulk properties of the Earth. Now, in these systems, we do exactly the same. We have small bodies that form a debris disk, accrete onto the white dwarf. We take a spectrum, we see metal lines, and we measure abundances. And I show you just two examples, and you don't need to know anything about spectroscopy of stars. This is two different white dwarfs, and without any prior knowledge, you will say they look very different. The reason is that this star at the top is a white dwarf that accretes calcium, titanium, and sodium. Now, these are elements found in the crust of planets, whereas the star at the bottom accretes iron and nickel, which are found in the core of planets. And so these two different stars give us two different examples of white dwarfs accreting a core fragment and a crust fragment. And that means we can study what planets outside our solar system are made out of, or the fragments of these planets. And you can see in the periodic system all the elements that have been detected by that study. And we can do some very simple statistics. And this diagram is a little bit complicated, but all you need to take away is that the line at 1, the dotted line, means that you would have material that is identical to the average composition of the Earth. If you have measurements for an individual element that sit above, then that system will be enhanced in the given element. If you have a measurement sitting below, it is depleted. So just keep that plot in mind, because it becomes important in the next and last brief section. And so again, a lot of what we do is data driven. So we get spectroscopy, and we study spectra, and we have a spectrum like this one here where we see, well, there's an H-alpha emission, hydrogen. There's some features here, they're just buried in the noise, but it turns out what we see here is lines of oxygen and sulfur. And so we had never seen sulfur in any of the stars before in emission. And so that took quite a bit of time. This is a better set of data. So you see there's lines, and if you look close, they're double peaked. Okay, so I showed that before. You know, there's a disk of gas, but rather than metals, calcium or magnesium or iron, we see sulfur, which is a volatile. We don't see any calcium. Like the gray line here is the system I showed before, just for comparison. So we see hydrogen, oxygen, and sulfur. And we see the same elements accreting into the white dwarf. And if we look at an abundance plot, the only three elements that we detect is hydrogen, oxygen, and sulfur, and they're overabundant by large amounts compared to the Earth, and all the metals are depleted. And so with some head scratching and going into the library and picking out books about the composition of bodies in the solar system, we came to the conclusion that we see H2S, hydrogen sulfide, and water ice. So we see hydrogen, oxygen, and sulfur. We're not very sensitive to either carbon or nitrogen, but what we see here is the atmosphere of a planet, a giant planet that is close to the white dwarf and that is heavily irradiated by high energy photons, which drives mass loss from the planet. And that gas from the atmosphere forms a disk and is accreted onto the white dwarf. And so some very, very simple qualitative theoretical model is that the mass loss of a planet is proportional to a number of constant, and the amount of extreme ultraviolet photons, so photons that can ionize hydrogen. And once you ionize hydrogen, you drive a wind, an outflow from the planet. And now this white dwarf is relatively young and it's hot. And so with almost 30,000 degrees, most of its photons get emitted below the Lyman limit and photoionize. And so what we found here is a planet at a distance of about 10 solar radii that is photoevaporated by the hot white dwarf. And now you may say, well, that was within the red giant. That planet shouldn't be there. And that means you can not only perturb small asteroids, rocky bodies, but in some systems you have, say, Jupiter or even heavier planets than Jupiter that may perturb something like Neptune onto an orbit close to the white dwarf, where again tides will circularize its orbit and lead to photoevaporation. And now I come just back as the final slides onto the solar system. You imagine the future evolution of the solar system. The sun becomes a red giant, evaporates, Mercury, Venus, probably the Earth. Jupiter moves out from 5 AU to about 10 AU. The sun, this is what we call a Hertzsprung-Russell diagram. This is the evolutionary path of the sun. You have temperature in log, and you have the luminosity, the brightness. And this is a log scale. So the sun currently has a temperature of around 6,000 degrees, and it has what we call a solar luminosity. So we just normalize to the luminosity of the sun today. It will become a red giant, so it becomes cooler. That's why the track becomes red. It loses half of its mass in a planetary nebula and exposes the core, which is incredibly hot, several 100,000 degrees. And the reason for that is that's the core, previously nuclear burning core of the star that shrinks to Earth size. It's still hot from nuclear burning, and it releases gravitational energy as it contracts. And so the white dwarf is born around here with a temperature of several 100,000 degrees, and then it cools. It cools very rapidly. It cools from 80,000 degrees. This is the total age. In a million years, a few million years, down to 40,000 degrees. But for a couple of million years, it is incredibly hot, and it has luminosities 10 or 100 times higher than the sun now. And all those photons come out as photoionization. And now we can say, well, what's the flux that Jupiter at 10 AU receives in terms of photoionization? And we worked out that the photoionizing flux of a white dwarf of 80,000 degrees is many, many orders of magnitude larger than currently of the sun. And that means that the white dwarf that the sun leaves behind will photoevaporate Jupiter at 10 AU and drive mass loss. And so some of that material will accrete onto the white dwarf, and somebody, some alien astronomer in 7 billion years, may observe the solar system when the white dwarf is still very hot and detect atmospheric material from the giant planets photoevaporated and accreted onto the white dwarfs. And I leave you with just that summary. Most stars have planets, and many planets, moons, asteroids, comets will survive the transformation of the host star into a white dwarf. And evolved planetary systems around white dwarfs are detectable by metal enrichment, dust and gust disks, and transits. We can use these systems to measure abundances, both of rocky material and of giant planets. And these studies involve a lot of complex physical processes, in particular the tidal disruption process. How do you go from a stable orbit at several AU to a disk of dust, which then accretes onto the white dwarf? There's a lot of work to be done. And I'll stop here and take some questions.
If there are any questions. Okay. Maybe if the graph that you show, like the evolution of the star into like white dwarf, right? That is like the log graph here. It's good to know what happened in the like the repeated pattern, like it's
here
the right way. Yes.
So you go through shell burning. The core of the white dwarf becomes extinct, and it's a core of carbon and oxygen, and then surrounded you have a layer of helium, and then surrounded you have hydrogen. So the helium is extinct, it will contract, the hydrogen on top contracts. But when you contract, you release energy, gravitational energy, and you compress the hydrogen, heat it up, and eventually the hydrogen layer will start to burn again. So then you have shell burning of hydrogen on top of a helium layer. That means you rain helium ashes into the helium layer, and the helium layer grows in mass. And so that will heat up at the bottom, and eventually helium ignites. And that is a very rapid, unstable process. So you get a very quick burning of the helium layer, which causes these flashes. So the helium gets burned into carbon and oxygen. It extinguishes everything. The star makes a little pulse. And then the hydrogen settles down. So all the helium is gone. You have a carbon and oxygen core. Hydrogen settles, ignites, produces a new helium layer. And stars can do that a couple of times until finally they evolve into the planetary nebula phase.
If there is no any question, I would like to say thank you for speaker. Thank you very much for the good talk today. So before we finish the section, and as a token of appreciation, I would like to present you a gift. But, probably waiting for the director.
The master of the ceremony has come.
Wait for the director to. Okay, for all the audience, we have like a satisfaction survey. At the end of the talk, can you please fill in the survey? Okay, the link for the audience online is on the comment section on the YouTube. For the audience here, we have like QR codes. So, as I said, as a token of appreciation, I would like to invite the director of the Institute for Fundamental Study, Dr. Narongrit Manijirapakan, to give speaker.
All right. I would like to say thank you for great talk to the professor. Okay, I'm sorry. I have the others, other training, and then the other rooms. Okay, and anyway, I think I would like to give a special thanks for Doctor to give a talk for us today and give our student for the knowledge of the dwarf, the white dwarf. Okay, okay. And I would like to give you some souvenir. The T-shirt of IF.
Thank you very much.
Okay, thank you very much. I hope you fit for you.
I think it will, yes.
All right,
It's
you
good.
can
Makes
change
sense.
if not big enough.
Thank
Okay.
you very much. Thank you for your attention. I know it was a little bit off topic for most of you probably, but I hope you found some interesting aspects.
Okay, give a big hand to him again. All right. Okay. I hope that you join in the near future. All right.
Yeah.
Okay.
Thank you.
Thank you.
Okay. Yes, you're welcome. Thank you for the invitation. Yeah. Yes. The effective temperature. So if you have the spectrum of the star is